Now, dear children, we will go to the next topic, almost the last topic. Okay, a very short chapter, as I said already. Okay, and the topic that we discuss is standing waves, also called stationary waves, in a string fixed at both ends. Now, this is basically happens under the string instruments. Okay, like violin, sitar, guitar. Okay, these are the string instruments which vibrate with different frequency. Okay, and the mode of vibration produced in a string is depend upon the position where we plug the string. Okay, now for that, what type of wave basically produces the standing wave or stationary wave? Okay, now for that, let us consider a uniform string. So this is a uniform string which is connected, okay, of length L. So from one end to other end, the length is what? L. So I consider the x equals to 0, say, and x equals to L. That means the string is connected on the horizontal x-axis. Okay, on the x-axis. So whose one end is, say, 0, say x is 0, and other end is what? L. That means the total length is how much? L. Now this string is connected and stressed by a tension, certain tension, between the two fixed points. These are the rigid support. Okay, whose and one end, as I said, is x equals 0, and other end is x equals to what? L. Okay. Now, when the string is not in vibration, means when we are not making this to vibrate, the string remain in what position? In mean position. This is the mean position. Means no vibration of the string. This is no vibration of the string. Okay, no vibration. That means the string is not set into vibration. So when the string is not set into vibration, then definitely no standing wave and all will produces. Okay, that means there is no frequency under this condition. But if I make this string to vibrate, okay, then we can make the string to vibrate in different modes. So now we do the different mode of vibration of string. So let's start with the first mode of vibration. So let's start with the which mode? The first mode of vibration. So if I have to make the string to vibrate with the first mode of vibration means the vibration of fundamental frequency. The string which vibrate with which frequency? A fundamental frequency. So in order to do that, I'll take the same length of the string. Okay, and I plugged the string at the middle point. So if I plug the string at the what point? Middle point. So from this mean point, okay, the string vibrate in this manner. Say the string vibrate in this manner. So when string is made to vibrate in such a manner, so if I plug the string at the middle of the length, then the string will vibrate with such a frequency so that there will be a two note formed at the two end, because these are the fixed end. The note is formed, one note and another note is formed, and there is one antinote formed at the middle. This antinote formed at the what? Middle. So under this case where the string are connected to both ends and made to vibrate, okay, by plugging at the middle in such a way so that there are two notes which form at the two rigid support end or fixed end, and there will be a note, max antinote, which form at the middle point, and such vibration makes to calculate the vibration of what? First mode of vibration, and this first mode of vibration is also called the frequency of fundamental frequency of vibration string. So we calculate the fundamental frequency of the string, okay, under this mode of vibration. That is called first mode of vibration. So under this mode of vibration, children, if you look at this diagram, this is the first mode of vibration. The distance between the two note, okay, that is the vibrating length between the two note, is equal to the length of the string. That means this length is L again, but the length of the string is also equal to the vibrating length between two notes, or distance between the two notes. You know, distance between two notes is always expressed by lambda by 2, and I consider this time the wavelength will be what? Is lambda, okay, and the distance between two note, as you know, is given by lambda by 2, and that lambda by 2 equals to what? L, because the length of the string is equals to L, so that lambda equals to 2L. So what is the wavelength under the first mode of vibration? Equals to 2L. Okay, how much? 2L. So remember this, lambda is the wavelength of the vibration, okay, and this wavelength lambda equals to 2L. That is 2L means the what? 2L is the length of 2L means twice the length of the vibration. Means the mode of vibration takes place under this case with a wavelength, and that will be 2L. How much? 2L. Now when there is a wavelength, then there is a frequency. Now I write down, let B be the speed of, B be the what? Speed, the speed of the standing or speed of sound wave. This is usually the speed of sound wave, because what is producing out here? Sound is producing. Okay. Now if this is the speed, then this speed and the frequency and the wavelength can be expressed by each other. Okay. Now we know the frequency means nu or n. You can write any of the symbol. Frequency can be written as nu or n equals to speed by wavelength. Children, is your convenient that you can write the symbol of frequency as nu or n? Your wish. Okay, any of the symbol can be used. So for your convenience, we can use n also, no problem. Okay, so I write down n equals to b by lambda. Now b by lambda is how much? Lambda is 2L. Okay, but you know that in a stress string, the speed of the what? Transverse wave or standing wave in a string is given by, okay, is given by how much? Square root of what? T by what? M. Square root of T by M. And this is by 1 by 2L. So look at the relations. Say I have written, replace B, small b by square root of T by M, where T is the tension and M is the mass point length. Or you can also write square root of T by what? Nu. So children, any of the symbol you can use. For mass point length, you can use M or you can use nu. Okay. The frequency you can write by nu, or you can write what? N. So let me just use n, no problem. Okay, so n equals to 1 by 2L square root of T by what? M. Now if I write this n equals to n1, and I am representing this n by n1 means this is the frequency. I represent this f, n1 is the frequency of first mode of vibration. First mode of what? Vibration. Because this frequency n can be for any mode of vibration, but to represent for particular mode of vibration, say first mode of vibration, n can be written as n1. So that means I replace n by n1 equals to 1 by 2L square root of T by M. So look at the expression of the frequency of stress string on the first mode of vibration. And this frequency is also known as fundamental frequency. So children, this frequency is also known as what? Fundamental frequency. That means to calculate the sound of frequency under the stress string, vibration stress string under fundamental first mode of vibration, then we calculate by this formula. That is 1 by 2L square root of T by M, or mu also. Okay. So under this case, the sound note which produced by the string is also called fundamental tone. The sound which produced is under what? Fundamental tone, or we also call as first harmonic. Also known as what? Harmonic? First harmonic. Now to get sound of first harmonic or fundamental tone, okay, we have to make the string to vibrate by plucking at the middle, okay, so that the string will vibrate with a fundamental frequency, and this is the fundamental frequency, and this fundamental frequency is the frequency under first mode of vibration. Similarly, we can do for next mode of vibration, that is called second mode of vibration. Okay. Now in second mode of vibration also, we make the string to vibrate in such a way so that if we make the string to vibrate at a length of 1/4 of its length, okay, total length from one end, then the string vibrate in such a way so that it acquire a frequency of tone, and this tone is also called first overtone. We also call first overtone, okay. But in this case, the string will vibrate in this manner. Say string will vibrate in this manner. Okay. So under this case, see, this will be note. This is note on this. Sorry. There will be a note which is formed at the middle, and there is antinote which is formed even between these two notes. So two antinote which form and note which is exactly formed at the middle makes the string to vibrate under second mode of vibration. This is the second mode of vibration of the string. So under this mode of vibration also we can measure the frequency. So to measure the frequency, as you know, the condition is vibrating length. The vibrating length must be equals to the length of the what? length of the string. Length of the what? String. See, children, in this case, you know that the string length is not changing. But the vibrating length, as for the case, the way the string are vibrating are changing. Okay, so that can be easily calculated again. So note and note distance is there. So we know note and note distance is lambda by 2. So it is lambda by 2 plus another note and note distance is also there. That is what? Lambda by 2. So I didn't do anything. So I just made the condition that distance between two note is always lambda by 2 and distance between these two note is also lambda by 2. This plus this distance is L. That equals to what? L. So the vibrating length is nothing but distance between this note and this note and distance between these two notes. So lambda by 2 plus lambda by 2 equals to L. Now take LCM. The LCM is 2. So it will be how much? 2 lambda equals to L. 2 lambda equals to what? L. If 2 lambda equals to L, then we can simply cancel 2 and 2. So that means L equals to lambda equals to L. Now this time the wavelength of the sound wave will be exactly equals to length of the what? String. Length of the what? String. So under this case also we measure the frequency. And you know frequency is N equals to B by lambda. So children, you can use any symbol. Either you can use nu or you can use N. Okay, let me use N, no problem. Okay, so frequency equals to B by lambda. Now B is usually known as B T by M, because even if you make the vibration on the second mode, but the speed in which it travel and produce the sound will be same. It's given by same formula, square root T by M. The speed will not change. Okay, so only the length, wavelength is changing. Due to that wavelength, the frequency is changing. Okay, but 1 by lambda is how much? L. So N equals to 1 by L. Okay, square root of what? T by what? M. Okay, but I consider for second mode, if N equals to N2. So I am representing by a particular frequency. For second mode of vibration, the frequency, if I write by as N2, this is the frequency of what? Second mode of vibration. Mode of vibration. If I write N2 is the frequency of second mode of vibration, then this N can be replaced by N2 equals to 1 by L square root of T by what? M. So now you can see N2 equals to 1 by L square root of T by M. This is the frequency of the second mode of vibration. But we can compare this frequency with the fundamental frequency. And okay, in order to compare this, let me just write it down. So let me just multiply by 2 in the numerator and denominator. So 2 by 2L square root of T by M. Now the reason I am doing this way, because 1 by 2L square root of T by M is nothing but N1. So N2 equals to 2N1. Now children, you can clearly see that the frequency of second mode of vibration is twice the frequency of first mode of vibration, or the frequency of twice the fundamental frequency. Okay, because this 1 by 2L square root T by M we have already done in the first mode of vibration, that is equals to N1. So from here I can make a conclusion that the frequency of the tone emitted from the string in the second mode of vibration is twice the frequency of the fundamental tone. And this tone is also called we also call as first overtone. First overtone. But in case of harmonic, on the order of frequency, it is second harmonic. So children, this word harmonic is represented on the basis of the frequency compared to the fundamental frequency. Because frequency of second mode is twice the fundamental frequency, that's why this harmonic is also called second harmonic, or we also call as first overtone. Now this is the second mode of vibration of stress string. Now we will do the last mode of vibration, and from there only we can make a conclusion. Okay. So the third mode of vibration can also be observed in the stress string fixed at both ends, and this mode of vibration can be done by plucking the string at a length of 1/6 of its length from one end. Okay, so under this case, the two notes are always formed at the two ends. Yes, you can see two notes are always formed at two ends. But other than two notes, there will be two more notes which is formed between the string. So one note is outer, and there is one more note. Whereas you can see in case of second mode of vibration, other than two notes, there is one note, okay, at the middle. But in third mode of vibration, there are two notes at the end, where there are two more notes which is formed at between the end. Okay, so that means these two are the notes. But between note and note, there will be what form? Antinote. Outer also antinote is formed. There is also what will form? Antinote is formed. So you can see in third mode of vibration, between two notes, there are two more note which is formed, and there are three antinote which is formed. Such mode of vibration is called third mode of vibration. So under this third mode of vibration also we can measure the what? Frequency. Okay, we can measure the what? Frequency. And the frequency can also be calculated in the similar manner. So I write down the vibrating length. What length? The vibrating length is equals to what? The length of string. The length of string. Now vibrating length we can do in the similar manner. Note, note, again note, note, again no note. So that will be lambda by 2. Distance between two note is lambda by 2. Plus again this two note is also lambda by 2. Plus distance between these two note is also lambda by 2. Equals to the total length is how much? L. See, string length is not changing. We are keeping the string length same. But the note in which the vibration occurs under this case are changing. And due to that, the frequency is changing. So children, you can see that it is lambda by 2 plus lambda by 2 plus lambda by 2 equals to L. Now let me take LCM on the numerator left hand side. LCM is 2. So it will be 3 lambda by 2. Because this lambda, lambda, lambda add 3 times. So 3 lambda by 2 equals to what? L. If 3 lambda by 2 equals to L, then lambda equals to 2L by what? 3. Yes, we can write lambda equals to 2L by 3. So with this lambda, the wavelength, we can measure now the frequency. Now the frequency N equals to B by lambda. Okay, B means same, square root T by M only. But this time the wavelength is how much? Lambda wavelength is 2L by 3. So this 3 will go in the numerator and 2L will come in the denominator. Because if I divide this quantity by 2L by 3, then this 3 will go in the numerator and 2L will come in the denominator. Okay, but we are dealing with which mode of vibration? Third mode of vibration. So I write down N equals to N3. This is the frequency of, this is basically the frequency of third mode of vibration. Third mode of vibration. So for third mode of vibration, the frequency I represent by symbol what? Symbol what? N3. So I write down N3 equals to 3 by 2L square root of T by M. Now this frequency can even compare with the fundamental frequency. You know why? Because this quantity, even in the expression you see, 1 by 2L square root 2 by M is actually nothing but N1. That means N3 equals to 3N1. See, N3 equals to 3N1. What do you mean by this? The frequency of third mode of vibration is 3 times the frequency of fundamental tone or the fundamental frequency. So in a stressed string, when it vibrates, the frequency of the emitted tone, okay, in third mode of vibration, that is N3, is 3 times the what? The fundamental tone. The frequency of the fundamental tone, also called fundamental frequency. And this particular tone in which the sound it produces is also called second overtone. Second overtone. Or we also call third harmonic. Third harmonic. Now from here only it is clear that in case of vibration of stress string at both ends, all the string are vibrating. String vibrates with all the tone. Odd vibration also takes place, and even vibration also takes place. Means it vibrates with odd harmonic also, and it vibrates with even harmonic also. Okay, that's why we can make number of conclusions, and the conclusion are all harmonics are present in the vibrating string. So if you look at this mode of vibration we discussed, okay, in case of stress string which vibrates, okay, all harmonic are present. That means all harmonic means the vibration of stress string consists of even harmonic also and odd harmonic also. Okay, that means all harmonic are present in vibrating string. Okay, next, the formula that we use, okay, to calculate is the frequency of the stress string. Okay, and this frequency we measure in terms of what? We measure in terms of what? Wavelength. And this wavelength and the frequency that we measure in terms of length of the string and tension and the mass per unit length of the string. But children, you notice that when we made the string to vibrate with different mode, it is actually done by plucking the string at different length of this different length. Like to get fundamental frequency, we pluck the string at the midpoint. Okay, midpoint of the middle length of the what? Wire or string. To get the first mode of vibration or second mode of vibration, we pluck the string at one fourth of its length. Then third mode like 1/6 of length, and it will keep on going like this and on. Okay, so this frequency, the frequency sound of frequency produced in different with different harmonic in a string instrument is actually produced by plucking the string at different length of the string. That's why we can write the frequency of fundamental tone and the overtone of a stress string by the ratio, and the ratio is 1:n1 n2 n3. Yes, it can go on is equals to how much? 1:2:3 ... like that. That means in case of stress string, when it vibrate, okay, at both end, fixed at both end, we get all the harmonic, even harmonic and odd harmonic. That's why the frequency mode can be written as n1:n2 equals to n3 ... It will be 1:2:3:4. It will go on and on. That means these frequencies are in a harmonic series. Hence, these tones are also called harmonics. These tones are also called harmonics. That's why the fundamental tone is the first harmonic. Okay, fundamental tone is the first harmonic. That means fundamental tone is the first harmonic, means the frequency is n1. Okay, then after we have first overtone. First overtone is nothing but the second harmonic. The frequency is n2, and second overtone is the what? Third harmonic, that is n3. Okay, and it will go on and on. That means we are getting all the harmonics. Okay, even harmonic and odd harmonic in case of vibration of stress string, both at fixed end. Both are connected with string are connected with two ends which are fixed. Therefore, the stress string gives both even and odd harmonic. So these are the detailed explanation I've done for the standing wave, okay, of stress string fixed at both end, or also we call as mode of vibration produced in stress string fixed at both end. Thank you so much. So with this topic, your chapter, the chapter is completed. Thank you so much.